I'm Andy. I'm a software engineer over here at TripleCyber. I work primarily on all the crypto library integration and in providing build and infrastructure, cloud integration, DevOps integration for the TripleCyber team. And we're here, I think, today to talk about cryptography. We got a whole group around here with me, but you guys get to watch me. So when you have traditional, we call it classical cryptography. That's based on values which are ultimately stored as zeros and ones, individual bits of information on electric charge. When you're talking about post-quantum computers, which is the heart of post-quantum cryptography, the big difference is that all of a sudden you're not limited to just 0 or 1 for your values. You can have multiple values simultaneously. What this really means is that a particular problem, such as solving a maze or coming up with the factorization of very large prime numbers, which can be very, very difficult for classical computers to do because they have to execute one set of instructions at a time, becomes theoretically much easier for a quantum computer to do because a quantum computer can ultimately take what appear to be, for example, in using a maze analogy, solving every path at once. The way to think of those paths is to think of values that are stored in what are called qubits. So the 0 and 1 that I described for classical computing is called a bit of information. A qubit of information, on the other hand, can have multiple values simultaneously, and the power of a quantum computer really can be determined by the number of qubits that can be processed by a computer chip simultaneously. So the more qubits you have, to use my analogy of a maze, the more paths that can be solved independently at once. With classical cryptography, the way that it works is you take a difficult math problem and you solve it, or you solve it in such a way that it is very easy to solve in one way and very difficult to go in reverse. So one way, as I pointed out before, is factorization of very large numbers. That's super simple if you know what the very large numbers are, the prime numbers are that you are multiplying together, but not so easy for classical computers to come up with what those prime numbers originally were. In fact, that's the whole basis of what we call RSA, or Rivest-Shamir-Edelman cryptography. And then there are other classical cryptographic examples, such as elliptic curves, which are based on the difficulty of defining the slope of a curve for a given set of numbers, which is very easy if you know what the given set of numbers are, but not so easy if you don't know what the original numbers are. And theoretically, those are much easier to solve through post-quantum computers. I say theoretically, we're going to come back to that a lot because we're in a state of flux and uncertainty. Very simply put, a PKI consists of the ability to exchange information securely between two parties. So if you have Andy and you have Brian, and Andy and Brian want to exchange data in such a way that somebody looking at that data being exchanged in the middle, or we call that a man in the middle, or watching the data as it traverses media, can't get to the information. And the way that happens, well, we talked previously about the difficult mathematical algorithms that you apply to different numbers. And so what happens is that in public key cryptography, you actually, for each key that you have, it's one key, but it has two parts to it. It has one part, which we call the private key, and depending on the underlying algorithm that you have, we'll use RSA, that can be a whole set of numbers that ultimately represent the multiplication of very large prime numbers. And then you have a private key, public key and a private key. They have a relationship to each other such that you can perform operations using the private key that only the public key can decode, decrypt, or understand. Also, conversely, you can take the public key and apply mathematical operations to it and do it in such a way that the resulting value can only be decrypted or decoded, validated easily by the other side that has the private key. So what happens with PKI is that ultimately it is about exchanging data between two parties. One party has the public key and the private key and shares the public key with the other party. The other party can also have their own public and private key and share their public key. Where we talk about PKI, because PKI really stands for public key infrastructure. Where the value of a PKI is that it wraps these public and private keys, well, not the private keys, it wraps the public keys into a registry. Not only that, but there is a whole mechanism around the public keys to wrap up the value of these public keys into what we call a certificate, specifically an X.509 certificate, which is a way of organizing data such that, for example, you'll have a name of somebody, like Andy. You'll have an organization, you'll have contact information, you'll have the public key. You'll also have something called a signer, which we'll get onto maybe a little bit later on. But the problem with PKI is that you must have this signer that I touched on for a moment. In other words, a middleman, a trusted intermediary that has a database of all these public keys really wrapped up in certificates, so a database of certificates, each one containing a public key. And it costs money to get these particular certificates. Not only does it cost money, but depending on the application that you're trying to use, such as encrypting a document in Microsoft Word or sharing documents via email, there can be what can be irritating configuration. So not only do you have a middleman, such as GoDaddy, you have the irritation of actually using the public keys, or public key combinations. And with TripleCyber, we eliminate that. You don't have the certificate per se. Instead, we have the registry of all public keys. Upon request, in other words, from a programmatic query, the consumer can actually get information about that public key. In fact, much the same information that you would get from a certificate, but it's much less overhead, and in our opinion, much easier to deploy and to use. Plus, we are working on, and we have developed a whole series of applications and add-ins to make sharing documents, because really, with public-private key, with a public key infrastructure, you're talking about verifying, for example, with a web browser to a web server that you're actually connecting to the website that you need to be connected to, but also, at its heart, exchanging data between two entities, A and B. And with our solution, we believe that we make performing those basic functions of exchanging data securely between two endpoints, we think we make it much easier. Well, that's like saying, why are cars being made faster? Why do we have electric cars if they can catch on fire? Why do we have gas cars if they can run out of gas? It's technology. Technology can be used however the technology is going to be used. The main difference with quantum computing, as I said, is that you have the capability of performing some operations theoretically much faster than a classical computer. I keep coming back to theoretical because we don't have quantum computers in wide operation yet. We are not 100% sure what algorithms, by algorithm I mean what special mathematical relationships that we would use to apply to information to be able to share it between two parties. We don't 100% know that the algorithms that we think will be quantum resistant are going to be quantum resistant. We don't 100% know that the algorithms we currently use, classical cryptography, will actually be affected by quantum computing. However, we know that theoretically, quantum computing can possibly take let's take an example. So if I take a typical web server certificate, and we'll call that RSA 2048, which is just a way of saying we're going to have a very long 2048-bit key stored as part of an X509 certificate that a web server presents to a web client. Okay, so if I wanted to pretend to be that web server, one way to do it would be to present a fake, or to basically be able to take an existing X509 certificate, which contains only a public key, and derive what the private key is. If I can do that, then I could pretend to be that web server, and it would be difficult, if not impossible, for anybody else to say that I wasn't that web server. How long would that take us to do with a typical laptop? About 19.8 trillion years. So a long time. We don't have to worry about that. It is estimated that a quantum computer that can have 372 qubits, so that's 372 simultaneous operations being performed on this secret key simultaneously, not like with your typical classical computer that would try a whole set of one numbers, then a whole set of another numbers. No, you're trying all numbers at once. About 8 hours. So that's now, and the current state of the art for a post-quantum computer, I think IBM has got a chip that has 1,172 qubits. So theoretically, that could happen now. It hasn't happened, but theoretically it could. So what we need to do as practitioners is make sure in government and finance that we're addressing that problem and taking steps to remediate the danger that it presents. A PKI infrastructure is important because it enables every financial security operation that we currently perform on the internet. The way that it works is that a full public key infrastructure consists of many different parts. At the very heart of it, you have a public-private key, where the public form of the cryptographic key is actually saved in the PKI, in the infrastructure, and the private key is retained by the owner of that private key and presumably is never lost by that owner or never compromised in any way. But a full PKI consists of a lot more. So as I mentioned before, within a PKI, you don't actually store the raw public and private keys, which is what we do in TripleCyber. Instead, what you do is you wrap the public keys inside an X509 certificate, and you have a certificate registry, which is a database. To manage that registry, you have what is called a certificate authority. That certificate authority is itself has its own public-private key and has its own trusted certificate. And by trusted, I mean that every single browser in the world, every single computer in the world will have a list of trusted certificate authority X509 certificates. That's called the certificate root chain. And depending on whether you're in government or you're in DoD or whether you're in private industry, there are different root chains that apply based on where you are. For the vast majority of us in the commercial sector, it's going to be the commercial list of CA, of certificate authority. So GoDaddy has one, but there are a whole series of them, a lot of them, and they're around the world. So you have the certificate authority, but it's not just that, because if you only had one certificate authority that had to do everything for every user on the planet, that's not going to work very well. So instead, you have the concept of a certificate authority at the very tip top, like if you're drawing a pyramid. Then further down, you have a little tree down here, and underneath that, you'll have these things called registration authorities, and you can have multiple registration authorities. The job of a registration authority is to take a request. So what happens? We at TripleCyber.com, just like every other website owner in the world, we buy a domain name, TripleCyber.com. We create a certificate signing request, or a CSR, that contains the public key of a public-private key pair that we created, contains information about who we are, what our contact information is, and contains other information which we won't get into, such as the usage for this particular certificate. And then we take that CSR and we submit it to a registration authority. The registration authority's job is to accept the request, use the certificate authority's private key to actually sign that request. What does signature mean? Digital signature is something that, much like any other mathematical operation, you take data, such as my public key, maybe my domain name, maybe other things, put it all together as a message, and apply ultimately a hashing function or a cryptographic function, which can be thought of as combining multiple colors of paint. So you get a color out, but very, very difficult to get the color back. So in other words, a digital signature is applied to a bunch of data to come up with a specific, in my analogy, paint color. However, it's going to be difficult or impossible to deconstruct that without having the appropriate other side of the key that was used to create that digital signature, which also, in a nutshell, explains the big problem with quantum computing. If quantum computing could actually take that paint color and resolve it back into its individual bits, well, then you don't have any security anymore, because we depend on that difficulty of undoing in our case, a digital signature. But anyway, for an X509 certificate, you end up with a digital signature that is returned by the registration authority to the requester as an X509 certificate. Additionally, you get the public key, or actually the X509 certificate, of the signer itself. So you have your X509 certificate, which contains another X509 certificate, your public key, information about you, usage of the certificate. That's what you actually present to web browsers or any other client. But we also have something, because we need to be able to handle the fact that a particular web browser, say, or a particular web server, such as TripleCyber.com, is presenting an X509 certificate to a web client or web browser. Well, that web browser needs to be able to know that it can trust that X509 certificate. What the web browser can do, it could certainly say, well, I trust it, but you don't want to do that now. What the web browser actually does is it takes a look at the expiration date, which is returned from the registration authority as part of the returned X509 certificate. It takes a look at the public key that was provided, and when I say the public key, I mean the public key for, in our case, TripleCyber.com that was provided, and then can perform cryptographic functions to say, is the digital signature that was created that is part of this certificate actually valid? So you can look at the expiration date, you can look at the digital signature and say, I trust it. But if you really don't trust the fact that there wasn't some clever imposter who's submitting an X509 certificate, but all the information about the registration authority, in other words, the public key or the X509 certificate of the signer is valid, then you can use the embedded X509 certificate to walk what is called the certificate chain. And ultimately, so you can have, because with a full PKI, you can have as many different levels as it makes sense to have. You can have a top-level certificate authority. You can have registration authorities, multiple of them. You can have multiple validation authorities. And you could have that at individual geographic levels. And if necessary, a particular client can keep what they call walking up the certificate chain to come to the top-level certificate authority, which presumably the client has got stored somewhere on the PC, because, as I said, every single device in the world will have this top-level list of certificate authorities. So a full PKI consists of all of these things and more. So, for example, I just mentioned that a web browser client could look at a particular presented X509 certificate and say, is the expiration date expired? Okay, well, if it is, that's fine. That'd be one way to tell. But what if the certificate has been revoked? In other words, what if somebody has said, we got compromised, we need, the certificate can't be trusted anymore? Well, in that case, you have to have the ability for a client to make a query and say, is this certificate valid or not? And that there's a protocol called OCSP, Online Certificate Signing Protocol, that provides that. There's a capability that a PKI can provide, which is called providing a certificate revocation list, or a CRL, which is a list of all the certificates that have been revoked. These are valid certificates that haven't expired based on universal time, but for whatever reason, they've been revoked. So a full PKI consists of a lot of different parts. I think I've mentioned a couple of different cases, so we'll go with the factorization of very large numbers based on multiplying very large prime numbers. And when I mean very large, I mean very, very large prime numbers. The way that that would actually work is that a particular value, such as a document that you want to sign or data that you want to encrypt, in other words, that you want to hide, is applied through a set of, they can best be thought of as boxes, where you have a box that says multiply this value by this number, multiply this, and then take that result and multiply it by another number, where the heart of it, the thing that you need to get started on going through these boxes, is the initial multiplication of the very large prime numbers. And it can be very expensive. As I was saying, for a laptop computer, it can be on the order of trillions of years to crack even what we would consider not the most secure, but a standard classical public key cryptography. You also have symmetric cryptography, and the difference between public key, private key cryptography and symmetric cryptography is that with public key, private key, there is one key, but it has two parts, a public portion and a private portion. I share the public portion with you, and I keep the private portion for myself. And using just that, I can exchange data with you on the other side. It doesn't mean that I trust who you are, but it does mean that I can share data with the other party without a third party being able to read it. With symmetric cryptography, there is a secret, such as we are king of the world. We could say that's our secret key. And I share that secret key with you. So I know the secret key, you know the secret key. I apply the same kind of cryptographic operations, the boxes, where you take an initial value, such as the beginning of the word, or you take all of the words together and you kind of multiply them together and divide them by whatever. You apply an operation and use the result of that to go to another box, and the result of that to go to another box. And at the end of the day, going through X number of boxes, you end up with a encrypted form of whatever data it is that you want to encrypt. So what post-quantum computing, the reason that it is effective against, or theorized to be effective against, classical computing, because with classical computing, you're talking about a computer chip that can actually perform one operation at a time, and if you want to perform multiple paths, such as, to use the analogy of solving a maze, if you want to solve multiple paths, well, first you have to use the computer chip to try one path, then come back to the beginning, try another path, back to the beginning, try another path. With a post-quantum computer, you can, in theory, try as many different paths simultaneously as you have qubits. In some ways, it's actually what post-quantum computing does is similar to what happens today with bit mining. With bit mining, if you're doing cryptocurrency, that actually happens because there are a large number of graphical processing units, or GPU chips, that you purchase, and you take a difficult mathematical problem and have a master control program that attempts to break that problem into its constituent elements and have each GPU chip solve a portion of that element. And in some ways, that's similar when back in the 80s and 90s, and they had the SETI research going on, and you could have your computer be part of SETI. It was the same kind of model, where you had 10,000 or 100,000 computers around the world, and each computer would be assigned a very small bit of processing to perform. Same thing with GPUs. In some ways, it is similar to what's happening with post-quantum computing, except that where a GPU, even though they're very expensive, they're actually pretty dumb and do very basic bits of work, which is why you have to have the master control program that can take a hard problem and break it up and have portions of the job submitted to each GPU chip. The quantum computer chip can perform all the operations. In other words, doesn't have to have a master control program to break up the difficulty of figuring out what prime numbers are, but can try every single path. Start at 1 and then move up from that and say, well, 1 didn't work, we'll go to 2, we'll go to 3. Do that with as many different qubits as the quantum computer actually supports. So you get enough paths that are done simultaneously, and you'll get the maze solved pretty quickly. It's the same operation as if I want to go through Red Riding Hood, going through the forest and taking the path, and there are 50 different paths. If I have 50 different Red Riding Hoods, how long will it take? It'll take as long as it takes one of those Red Riding Hoods to actually go through the forest. With a classical computer, you have one Red Riding Hood trying 50 different paths and then trying to figure out which maybe was the shortest path. That's easy, basically everything. So government, financial, internet, commerce, anything that log-on servers, anything, so corporations, anything that requires two entities to share data. So if I'm trying to log into a website, what I'm trying to do is authenticate myself to that website. That means that I've got a password or I've got biometrics, but I've got data which is stored that needs to be exchanged with the other side in such a way that a third party cannot read the data in transit, or if I have secure data such as my bank account information and access to the servers that control what my bank account information is, that would be called data at rest. And we want to make sure that even if you have data at rest, that a bad actor cannot attack that data and, given enough time, reverse engineer it enough so that financial operations could be performed. So you have attacks against data live, data that's being exchanged real time, and you have attacks, especially, for example, against government secrets, secret documents, secret plans, anything that needs to be kept secret needs to be resistant to quantum computing. So everything could be affected by quantum computing. It actually won't have that huge of an impact at a logical level if we think about it. It's going to have a tremendous impact on an actual level or an implementation level. But logically, what a PKI does now is store a public-private key combination. When you have post-quantum computing and quantum-resistant algorithms, you still have a public and private key pair. You will still store the public portion of that key pair in the PKI. So what would the PKI have to be able to do? You don't have to know about what these algorithms are. It's the same process that we use for classical public key cryptography. The devil is going to be in the actual implementation. No, that's the logical successor to the previous question. So, the devil is in the details. The big problem is that every single computer, every single device is going to have to be updated to support quantum-resistant algorithms. The big problem that we have now is that things are in a state of uncertainty and flux. We don't know for sure, that there's going to ever be any quantum computers that can actually perform the work that is being theorized. But we have to prepare for it, whether that actually turns out or not. Much like with Y2K, everything has to be examined, even if you're pretty sure it's going to be Y2K compliant. Well, you have to be totally sure because you don't want things falling out of the sky. And it's much the same effect with post-quantum. So what we have to do is, starting now in 2025, because that's when the current initiatives are actually running right now, within all the major governments, within the United States. We have the National Institute of Standards and Technology, or NIST, that has come up with a list of recommended post-quantum or quantum-resistant algorithms. And what we need to do as engineers creating products, or security engineers securing our company servers, or PKI providers, in other words, people with full PKI infrastructures, is to implement the post-quantum algorithms that have been recommended now, and to create updates for the operating systems for every device that currently runs, because almost every device, including even the back-end devices like network switches and routers, many of them are updated automatically, and those that aren't updated automatically are generally updated on a schedule. So starting in 2025, the big initiative is implement quantum-resistant computing. Even though it's still theoretical, and the post-quantum algorithms that have been selected may change, we implement the best solutions that we have now so that we can get all the other work done, all the underlying plumbing. That, for example, in our own software, we have to account for the fact that we can have more algorithms that we support. So we make sure that we can have that driven from data to say what kind of algorithm is actually being used by a particular key, so we can apply the appropriate cryptographic operation. And depending on who you are, what work would be done is different. So as an end user, well, which I think we'll get to in a moment, there's not much you do except keep your systems up to date. Potentially, because handling post-quantum cryptography can take more time than classical cryptography. There may be particular devices and actual underlying CPU chips that simply aren't going to scale very well in a post-quantum world. But as part of 2025, to investigate how our software needs to change, along with what the expected impact will be on all the devices that currently live out there. What you can do now is, for two audiences, for the end user or the consumer, you can keep your devices up to date. That's the best thing in the world. If your devices come back in 2026 and start to tell you, we're going to have a problem with this particular power of this device and post-quantum cryptography, there may be some added expense of replacing that device. But beyond that, for a consumer, stay up to date. For organizations, start to analyze the existing tools that are being used. So for especially a corporate or government institution, let's take the US DoD. They have a common access card or a CAC card. That CAC card has got a private key on it. That private key is going to be a classical private key. Well, that's going to have to be changed, and because these cards generally can't be written to again, they're write once, read many times, that means that over time, CAC cards are going to have to be reissued, and they're going to have to be reissued with quantum resistant keys, algorithm keys. Not only that, but the software, for example, that reads the CAC cards, the common access cards, or the PK the cards within government, that the actual hardware that is used to read those keys may need to be modified if the size of individual data fields changes on the card itself as a result. For example, using certain post-quantum algorithms can result in keys that are quite very much larger than their existing or their current classical algorithms. So both from the hardware side, from the software side, from the integration side, there's a lot that organizations and government can do now. The first step is to make sure that the underlying PKI infrastructure is itself being modified and updated. So, and for many organizations, for example, the US DoD, where they have their own certificate authority and certificate chain, there's going to have to be time, money, and expense allocated such that the PKI infrastructure itself can be updated, which is the same thing that GoDaddy will have to do, which is, I touched on changes that might be required, for example, for a common access card, for a smart card to be able to log in. And that wouldn't just be for government, because you have smart cards, you have these things called dongles that basically you plug into your USB port, but they are the equivalent more or less smart cards, but every single one of them. Anything that uses a public-private key pair will need to be addressed. And what organizations can do best now is to analyze what portions of their own infrastructure actually depend on public-private key pairs. For the vast majority of organizations, it's going to be who your provider is and whether the provider is actually performing updates on their software and what their time frame is and what their expected impact will be on current deployments. Our approach is that we basically eliminate the middleman on certificate management. So with our approach, either at the TripleCyber, what I like to call the TripleCyber consumer level, which would be the consumer cloud, you have a list of public keys that we maintain that we create automatically for each managed device. And by managed device, we simply mean a device that has been triple enabled with a TripleCyber application. These public keys are, as I said, created automatically within our own product offering. As of Q1 2025, we have full support for post-quantum cryptography already built in. And that in conjunction with the fact that we eliminate the middleman of a certificate provider without losing the ability to exchange data securely and to encrypt and decrypt documents as need might be, have encrypted conversations or chat. We think that we're doing pretty well and we're staying ahead of the curve. But the curve doesn't stop, so we have to continue working hard to make sure that we adapt to the evolving nature of quantum computing. Short answer, not right now, no. Long answer, every single government, including our own around the world, is issuing guidance. And there are many organizations, so I mentioned NIST before, but not just NIST, there's IBM, there's Microsoft, there's Google. All the major organizations and government entities are addressing the problem of post-quantum computing, and there's a large push for all commercial software providers, especially the big providers, to integrate post-quantum support in 2025, or at least to begin that support in a major way. So the same thing that we're doing in TripleCyber, we're looking at the same NIST special publications, they call them, in guidance for which post-quantum algorithms we should provide, what we should plan on doing in terms of this difficult period where there will still be vast numbers of devices that are not post-quantum capable. So in other words, we'll have to bridge a gap where a particular device connecting to a particular server might be able to use post-quantum, but may not be able to use post-quantum. So in other words, you have to do both. And just exactly how you do that, there are a number of technologies and approaches for that. One of them is called hybrid keys. So where you have a public-private key pair, up to now it's been a particular type, whether it's been a elliptic curve or RSA. Those are really the big two that are actually in use now. You have that particular public-private key pair, an RSA public-private key pair, or an elliptic curve, or EC public-private key pair. With a hybrid post-quantum model, what you actually do is you'll have two sets of keys. You'll have one key pair, but two sets of keys for that, two sets of key pairs for that key pair. One public-private key pair will be classical, and the other public-private key pair will be post-quantum, with the expectation being that the receiver will use the best fit available. So if the receiver only supports classical cryptography, then the classical algorithm will be used. If the receiver supports post-quantum, then the post-quantum key pair will be used. But both key pairs actually make up a logical single key pair. The only one is an unsubstantiated 2022 Chinese paper that posits that with a 372 qubit post-quantum computer, they can break an RSA 2048 key, which RSA 2048 is pretty much the industry standard for web servers. That would be a big problem. Actually, nobody believes that that really happened. It has not been substantiated by any other study or any other reputable academic or commercial organization. However, we take it very seriously that even if that is not currently, if it didn't actually happen and all of our RSA 2048 keys are safe, that provides, I think, the extra impetus and stimulus that has resulted in this using year 2025 to actually become post-quantum resistant throughout industry. I think that's a big driver of it, that there are nation states and other adversaries that are dedicated to making use of post-quantum cryptography in a way that can compromise data from more people around the world and more governments around the world. So while there are none that are documented yet, we are moving, I believe, in the industry very quickly. Now, 2025, just like in TripleCyber and our own products, we are implementing post-quantum support. All of the major vendors, all of the PKI infrastructures are doing exactly the same thing. I'm going to go on a limb here and say that the vast majority of web browsers and the vast majority of web browsers will be post-quantum compliant by 2026. I believe that for PKI, for a full infrastructure, that's probably going to lag for a year or two just because there are so many moving parts. I'm thinking 2026, 2027, you'll see the major infrastructures such as the GoDaddies of the world and all the rest of them, including the US government, will become post-quantum capable and ready to support by 2027. I think by 2030, we will see the vast majority of end-user systems updated. We'll see the vast majority of software updated. I believe that smart cards and security dongles of every type that are currently used will have their post-quantum replacement available and ready to be deployed. So by 2030, I think within 5 years, I think that 99% of the internet infrastructure will be post-quantum ready. I think that by 2035, which from what I understand is pretty much the earliest date that anyone gives for a real threat to emerge from post-quantum computing on classical cryptography, I think it will be the very rare exception that is actually susceptible to that attack, if it turns out to even be a valid threat.